Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Afternoon. My name is Ganesh. I'm a research assistant at the College of Oceanic and Atmospheric Sciences at Oregon State University. So basically, digital content is increasing rapidly, both in the form of video and still images. And also in the world of oceanography, there are all these programs underway to basically stream high definition video in real time from the bottom of the ocean to basically study the phenomena that are happening there. There's actually a program known as Orion that is basically the construction of a large ocean observing system. Universities like UCSD and University of Washington are also involved in this process. But the thing with high definition video is you really have to deal with large amounts of data, and manual approaches at finding and tagging content is eventually going to run into a roadblock. So our approach is to use existing industry standards as far as possible so that we don't have to reinvent the wheel, and then treat video as a data type rather than material that's just going to be viewed on like the Discovery Channel. So MPEG-7 is a multimedia content description interface. This means that it's basically a layer of metadata that sits on top of existing standards such as MPEG-1 and MPEG-2. But unlike those two standards, MPEG-7 is based on XML and XML schemas, and it's not really a video compression format. So it consists of something called low-level descriptors, also called visual descriptors. You do have audio descriptors, but I'm only going to talk about the visual aspects. Low-level descriptors basically go into the content itself and look at the pixel values in terms of statistical characteristics of things like edges and colors and so on. Description schemes, on the other hand, have more to do with the human perception of what's happening in a scene. So if it's a game of soccer and maybe there's a goal being scored, how do you define that event? You have to define what the goal post is, what the ball is, and so on. So low-level descriptors are basically just structures. Think of a descriptor as an XML file with these structures that talk about the distribution of edges, colors, textures, shapes, and so on. How you extract the descriptor is using what is known as a reference implementation of MPEG-7. So the reference implementation is, here is one instance of how we can implement the standard. And what they have is something known as the MPEG-7 experimental model. So that's the reference implementation. What it does is it takes either video in the form of frames or a still image, and then it generates this XML description that has all the statistical information that I mentioned earlier. So these are some of the examples of the low-level descriptors. You have something called the edge histogram descriptor. So you're basically looking at different kinds of edges within a sub-image. So you might be looking at vertical and horizontal edges, and also those at 45 degrees and 135 degrees. So what you do is you compute a histogram across sub-images, and you also look at the image as a whole. So you're looking at both the global and the sub-image level. In the case of the homogeneous texture, you're looking for patterns that repeat. A texture is basically a repeating set of patterns. In the case of color structure, you have a structuring window that actually moves across the image, and within that window you basically compute a histogram of all the colors that occur within that window. Color layout, on the other hand, is looking at the average of colors within a sub-image. And finally, motion activity is a way of analyzing motion in video. So what happens there is motion vectors that are built into MPEG-1 and MPEG-2 video can be extracted, and the magnitude and direction of motion can actually be estimated from that. And the descriptors are basically rotation and scaling invariant. So the search process consists of two phases. So in the first phase, you actually have to pull out all these descriptors given the content, and once the descriptors have been extracted, you can cache them, so you don't have to do it over and over again. In phase 2, the user provides basically a test image, like a query image, that is again subjected to the same process, and then the two sets of descriptors are now compared to determine how close they are. So the cache of descriptors that you have can be appended at any point in time. So if you have new video that's coming in, you just run it through the descriptor extraction process and append it to the existing set that you have. So description schemes again are really looking at the reality behind the content. So it's more from a human perspective. And the low-level descriptors aim to sort of find out, what are the objects and events in the content, and then the high-level description scheme can basically describe it in a more human readable form. And the search can be performed against these description schemes. So we applied MPEG-7 to develop a high-definition video search engine. So we took about 10,000 frames from 2.5 hours of video. This is actually at the rate of 1 frame a second, because if you do 30 frames, you get a huge amount of data. And typically, a lot of it tends to be redundant. The content actually came from a cruise that was sponsored by the University of Washington, in which they sent a camera down to the bottom of the Pacific Ocean to a depth of about 2.4 kilometers. And there are some pretty interesting things that go on down there, so it was pretty amazing. We also applied this technique to look for eddies and supercell storms in radar images. So the architecture consists of basically a .NET Windows form that has like a Windows media player, basically to look at the clips, and also different UI elements to pick the descriptors of choice. The form actually communicates with the SQL Server backend. So what we thought we would do is use something known as common language runtime integration. So this is actually a really cool feature in SQL Server, where you can develop stored procedures in languages other than SQL. So you can use C# or VB.NET. And then you can deploy the stored procedure into the database, and it gets treated like a regular stored procedure. So this actually helps in going beyond simple tasks that are suited only for SQL. So if you have any sort of image processing or something that goes beyond relational databases, this is how you get to extend the database. So this is again a pictorial view of how the search works. You have video or still images that goes through the descriptor extraction process, and then the descriptors are uploaded to the database through something called an HTTP endpoint, and I'll talk about that a little later. As far as the search is concerned, the user provides a query image, and the descriptor matching process is basically applied. So this is an example of how you create a stored procedure. In this case, it's actually a function by the name find using visual descriptor. So if you go down to the bottom where it says as external name, what's happening here is the SQL stored procedure is being associated with a function of the same name that's actually deployed in an external assembly known as MPEG-7 document. So that assembly actually has to be installed into the database and given the right permissions, etc. The next step is to actually take the stored procedure and expose it out as a web service. So SQL Server has this feature called an HTTP endpoint. And with very little code, you can actually take a deployed stored procedure and turn it into a web method. So if you go down to the last few lines where it says for soap, you're basically creating a web method that that's called find using visual descriptor, and it's associated with the stored procedure of the same name within the looking database. Things like authentication can be tweaked, so you can have instead of basic authentication, you can have integrated authentication and over clear ports, but then that's going to be insecure and it'll work only on your local machine. So if you want to do any kind of remote access, you have to use SSL. So the UI basically allows you to turn the video into frames, and then descriptors of your choosing are then generated and uploaded to the server. Once that's done, you have two approaches. There's something known as a retrospective search. So in this case, a user can provide an image that initiates the search. The descriptor comparison is again done, and then you could return, say, the top 100 or top 10 frames depending on the size of your cache. So this is an example of a retrospective search. So what's happening here is oh, sorry. The image right there on top is basically one that's not part of the stream. So what's happening is a user that provides his own image, the descriptor extraction process is applied, and then it's bringing back the set of images that were closest to that input image. And what's being used is actually the color layout descriptor. So it might be a little hard to see, but that's the descriptor we are using. The other thing you can do is apply to something called real-time event detection. So in this case, we actually don't have a large set of images. We have a much smaller subset that have things of interest. And then the query images are actually coming from a stream. So you're looking at a stream and then taking every frame and saying, have I found the event? Have I found the event? And so this continuous computation of the descriptors has to happen and compared on a continuous basis with the images that you have in your library. Once the difference falls below a certain threshold, you say that yes, the event has occurred. And that threshold actually has to be figured out. So I'll jump to the next slide. So this is actually a reference event. In this case, we are looking at this region right there. We are interested in every time a car shows up there, we want to detect that event. So this is actually an instance of an event. So what would have happened is the numbers that you see at the bottom here are constantly, they get updated as new frames are coming in, and those numbers basically are the difference in the descriptor values. So as soon as it falls below a threshold, it'll signal an event. So this is again two different approaches. In the first case, in the retrospective search, you have a large number of frames, and your query image is compared against these. In the real-time event detection, you have a smaller library of images, and the query images are basically coming from the stream. And once the threshold conditions are met, you can signal an event. So these days, since all these multi-processor and multi-core systems are getting available, you can actually divide up the frames among all the cores that you have. So suppose you have 10,000 frames and you have a 16 processor machine, you can basically take 600 frames and give it to each core, and then so the descriptors get extracted concurrently, and these are actually done using threads. So the threads generate pieces of XML, but the XML actually has to be put together in the right sequence. So the threads have to basically communicate with each other when they are done, so that you have a single large descriptor file at the end. So some of the challenges that we had were basically things like shadows, and also different times of the day you have lighting problems that lead to false positives. So one of the solutions is to look at the value of multiple descriptors. So if you just look at a single descriptor, you may or may not actually catch the event. Also, keeping up with a high definition stream at 30 frames per second is really intensive. So some sort of multi-core architecture would be a great fit there. And also, when you start looking at the descriptors for millions of images, as in the case of the web, you're soon going to run into problems where the descriptor file gets really large. So to conclude, MPEG-7 supports a really nice framework to execute content-based searches. Once the low-level descriptors describe the content, you can go in and build higher description schemes that would be more suitable in a human context. Some of the things we'd like to do in the future is basically look at GPUs to speed up the descriptor extraction, but most likely there will be some sort of porting that needs to happen in that case, porting of the MPEG-7 code. Also, we'd like to look at cloud services in the sense that you could have a real-time stream that goes into the cloud, and you have web services that automatically extract the descriptors and detect events, and you just have like a summary segment of what's happened today. And I think that would be a great fit, since virtualized storage and computation are basically the key there. And we'd also like to look at using the Surface computer as a UI. So to conclude, I'd like to thank the University of Washington Professor John Delaney for giving us the HD footage, and we'd also like to thank NSF for funding this project. And what I'm going to do is I'll try and do a demo. That's actually just the wallpaper. Okay, so what I'll first do is I'm going to search through some video based on images that I have. So actually, and I'm going to do a search using the edge histogram descriptor. Okay, so in this case what happened was, what I'm going to do is I'll just quickly pause this. It brought back a set of frames based on how close the input image is to the frames in terms of the edge histogram descriptor. And then what you can do is you can just click on one of these images and then go directly into the video. So this is different from using text to annotate video. So this is basically you're looking at tube worms at the bottom of the ocean. This is actually the event detection application. I guess there weren't any events that were detected today, but typically you could go back. I've had this running for a while, so okay, I guess there's some issue with the other application, but basically you have these reference events. Oh, I don't have those. Okay. Um, I'm looking for cars at certain points in the image, and basically you have like a car right there. And then I'm looking for heavy traffic at the end of the road. So like this is another event. So basically, since I don't have the reference events, I can't show you that it's basically working. But essentially, I'm looking for vehicles at different points in the image, and then doing the comparison of the descriptors, and then detecting the event in that manner. So this can actually be applied to many areas of science, and also like satellite images and those kinds of things. So thank you.
Thank you. I work with people who do who work on descriptors of images and also on videos.
Okay.
And they taught me, for instance, that descriptors for soccer matches, Brazilian soccer matches, are completely different, and they are useless for British soccer games, okay? Because of the semantics associated with the way they watch soccer in Britain and in Brazil.
Okay.
So how do you account for these semantic variations when you want to describe or to find good descriptors for videos? Are you considering that, or are you targeting specific domains?
Usually there'll be a mapping. When you move from one space to another, there would be a mapping of from one locale to another. So that translation would have to be done in order for the...
With a domain expert then?
Yes, yes. I think that all those scenarios have been accounted for in the standard, so it should be quite straightforward.
You mentioned about your thinking about using Greek clouds, but analyzing video images, it's a huge amount of data.
Right.
To transfer that to cloud, you need to special link, maybe even more cost will be to provide this link than analyzing. Can you comment on this?
I think that what can be done is you can have the stream coming in continuously, but you don't have to keep all the data. So you can basically focus on what it is that you want to keep, and then look only for those events, and then you would basically start recording when you saw something come by. So this is actually one of the problems that they face in the design of the ocean observatory. You don't have unlimited amount of storage or disk. So how do you deal with this problem? And basically these types of technologies would be the answer, where you look for specific things that you're interested in and only keep that. Although typically in the science world they like to archive everything, but I think at some point reality is going to set in, and you have to decide how much you want to keep.
So in the previous demo you did, you searched a video based on an image.
Right.
Can you search for pieces of the, does the image has to be the whole frame? Or can I search for example, a face of a person in a wider video where his face is not the full frame?
That's totally possible. In fact, in the presentation, I had the slide where you had like a polygon drawn around one of the cars. I don't know if you want me to, I can put it up if you want. But basically that was used as a mask. So what it does is it ignores the rest of the image. So I'm looking for a car only at that point in the image, and I'm not concerned about what's happening around.
Sorry, I mean the reverse. I'm looking for their car anywhere in the video, not, it is actually the reverse.
Okay, so in that case, you actually have to consider the image as a whole. So if there are different ways of doing matching the search. So in the case of the TubeWorm video, I'm looking at the two images as an entirety, so I'm not looking at pieces. You can apply the mask, but the mask, you could apply the mask to the input image, and you can search it against the entire archive. So you can, your search, your archived images can be treated as a whole. So you can actually mix and match. Whether that process is going to be effective, I'm not too sure. Since you're comparing different regions, so the matching is going to be a little different.
Okay, I think we should wrap up. We've got a short break now and then the closing plenary. So one more round of applause for all three of our speakers.